biaxial material, is all this?
No. If you can, just let that just yep.
Okay. So with the biaxial material, you've got your conoscopic image, and you're going to set it up so that the trace of the optic axial plane is in that direction. Here's the slow ray of my compensator. And if I know that the trace of my, what is it, basically, okay. So I will orient my conoscopic, my centered conoscopic interference figure. I will orient it such that I have the brushes or the isogyres in the second and fourth quadrants. Okay. If I rotate that, then they go back to being across. And the isogyres, you have the emergence points of the optic axes right at the center of the brushes. Okay. And I'm passing them around, but the when you look at the biaxial interference figures and you look at the points where the optic axes are emerging, remember you want to position it such that you have an acute bisectrix aligned with the light path of the microscope. The melotopes are the emergence points of the optic axes, and they also happen to be the center of the brushes when they're positioned like this. Okay. So if that's the case, and you're looking down at the biaxial interference figure, what you'll realize is that the emergence, remember the optic axes are on the yellow ellipse? They're on the yellow ellipse. So they're coming out that way. So what it tells me is that if my optic axes are basically coming out of the screen like that, that means that this line must represent that yellow ellipse, but looking down on it. And if I'm looking down on it, all I'll see is a line. Okay. Does that make sense to you guys? You can look at that and say, oh, it's, all I see is a line. But at these 2 points, that's where the optic axes are emerging. Okay. And the other thing you'll see, and once again, you might want to spend a little bit of time with the indicatrix figures to get it in there in your brain, is that if you know the alignment or the orientation or the trace of the optic axial plane, then you'll know that beta is perpendicular to it. Okay, and you can see that from the indicatrix figure. Yes. So when you're looking down on it, and the yellow line is what the optic axial plane looks like when you're looking down on it. It's just a line, right? Because you have to look up at it to see that it's a plane, an elliptical plane. Then you'll also see that the index of refraction that's perpendicular to that is equivalent to the beta index of refraction. Okay. And remember, the beta is in between the length of alpha and gamma. So it's the intermediary. Okay. So here is my biaxial interference figure. It's the negative optic sign in which I have my optic axes, which is the black lines. You can see those, the black lines. Okay. And it's an acute bisectrix figure because the acute angle is facing up and down. And the direction that's cutting that acute angle in half is the shortest direction, the shortest diameter on this indicatrix figure. And the shortest diameter represents the x direction in which alpha vibrates. Okay. So this is positioned on my microscope like this when I'm getting a centered interference figure. And so where these optic axes are emerging, that's where the melotopes are, and I'm going to have brushes like that, okay, on either side. So when that's the case, I'll know that this is the optic axial plane. The yellow line, when I'm looking from above, is the yellow ellipse. When I'm looking straight at it, when I'm looking from above, that's a yellow line. The optic axes are emerging right over here. And so that's my optic axial plane trace. And perpendicular to that over here, that is the beta magnitude. That's the minor diameter. Remember, the major diameter for the yellow and the red represents gamma, because it's the longest refractive index, the longest diameter of any of the ellipses here. Over here, the yellow plane, this is the shortest refractive index, so that has to, the shortest minor diameter has to be the smallest refractive index, that's alpha, and the one in between got to be beta. Okay, and you'll notice that that also happens to be the direction that's perpendicular to the trace of the optic axial plane. So that'll always be the case if you have a centered interference figure where the acute bisectrix is aligned with the light path of the microscope. So if that's the case, not the case if you got it differently. And in fact, I mean, there are more complicated things, but let's just start with those basics to begin with. So if that's my trace of the optic axial plane, then this is beta. And what I want to find out is this beta the fast ray or the slow ray? And if I'm looking at my indicatrix figure, I can figure that out pretty easily because I can see over here that this is the larger refractive index. It's the longer magnitude diameter. That's the trace of the optic axial plane. And the only one that's longer or greater magnitude than beta is gamma. So gamma is vibrating like this. Beta is vibrating like that. And the direction that's coming out is the x direction. The x direction is the acute bisectrix, which also makes sense because the line that you see cutting the angle in half is also the line in which the smallest refractive index, that's its vibrational direction. Which is not the case over here. Do you see the acute angles? And I know they've died a little bit, they've been broken off over time. Like I said, some of these figures are older than some of these optics, so you allow it to be a little bit older to decrepit. So it's got your optic angle, okay, and I've positioned in such that the acute angle is facing up and down, and the obtuse angle is facing side to side, okay? So when you're looking at this, it's positioned on the microscope. If the acute bisectrix is aligned with the light path of the microscope, then it's on the stage of the microscope like this. The optic axes are coming out, and those will be the melotopes that I see in a conoscopic image. The brushes will be, basically the center of the brush will be the melotope, okay? And so I can see from my indicatrix figure that if I can figure out that these brushes, the line that connects the center of that has to be the optic axial plane, then I'll know that this must be the beta direction, okay? That's beta. This is either alpha or gamma. But from my indicatrix figure, I can see that, oh, this direction's got the smaller refractive index compared to this one. And smaller refractive index, well, the only one, gamma's not smaller than beta. Alpha's smaller than beta. So I know that alpha is vibrating in the direction of the optic axial plane, the trace of it. And gamma is perpendicular to it. The other direction has to be the acute bisection, which is the z direction, like gamma vibrates.
So, if I'm correct here. So, the image for that, if you were to draw, what would you call that figure that you drew there?
That is a centered biaxial interference figure viewed conoscopically.
Okay.
Yeah!
So that would look different for this, because for this, alpha would be going through, not beta?
No, hold on a second. I have not defined whether this is a positive or negative optic sign yet. But for both of those situations, whether it's a positive or negative optic sign, if I orient it in such a manner that the axial plane is cutting through the second and the fourth quadrants, then beta, by definition, will be cutting through the first and the third quadrants, whether it's a positive or a negative optic sign. So the way I find the direction of the optic axial plane is I look for those isogyres, those brushes, those mellotopes are right at the center of those brushes. I connect a line to connect those mellotopes or connect the center of the brushes. That's the trace of my optic axial plane. Make a perpendicular line, that's beta.
So beta is always perpendicular to the
Trace.
Okay. So in this case, this would be beta?